Flaky tests waste software engineers' time and infect otherwise healthy test suites. In this video, I'm going to show you two examples of how you can identify, prioritize, and fix flaky test failures using Gradle Enterprise, a comprehensive solution for addressing your developer productivity challenges. Hi, I'm Eric Wendelin, Analytics Lead Engineer for Gradle. In our first example, we're going to use a data-driven approach to find and fix flakiness in a Spring Boot microservice application. First, we need to collect build and test information. We'll start by applying the Gradle Enterprise plugin to the Gradle build in settings.gradle. After applying the plugin, we configure the Gradle Enterprise extension to send build data to our self-hosted Gradle Enterprise server. We then configure the build to always publish build scan data, so that we can capture and analyze both CI and local builds. Next, we need to collect flaky test data. Gradle Enterprise uses an effective and easy to understand strategy for identifying flaky test failures. If a test fails and then passes when retried, the test's outcome is recorded as flaky. That means you can use any test retry mechanism, including JUnit retry rules, TestNG retry analyzer, or test rerun capabilities provided by Maven and Gradle. For Gradle projects, we recommend using the official Gradle Test Retry plugin, as it is a convenient way to enable retrying for all tests. After applying the plugin, we configure the test retry extension to rerun failed tests up to 2 times. We can choose to fail the build on a flaky test failure and encourage developers to investigate, or we can let the test pass to unblock developers in CI pipelines. Either way, using historical data to proactively and regularly fix the worst flaky test offenders is critical in order to avoid flaky production bugs and to improve developer productivity. With this setup, our Gradle Enterprise server collects build and flaky test data for all our builds in our microservice project. Let's visit our Gradle Enterprise server in a browser to see our build data. Gradle Enterprise provides various analytics on your build data, but today we're exploring test reliability, so we'll click Tests in the navigation bar. This test dashboard shows failed and flaky test trends at the top and lists the most unstable test classes below. You can bookmark this page so you have quick access and check it regularly. In order to report on test reliability for our project, we enter the project name in the filters above and click Refresh. Next, we check the trend charts to identify any recent regressions. The recent failed test trend does not look concerning because the overall trend is flat. The flaky test trend, on the other hand, shows a concerning increase in flaky test failures. 310 of the 26,000 total builds failed due to a flaky test failure. Test classes with the highest number of failed outcomes are listed below. To sort the test list by flaky outcomes, just click the flaky header. The top 3 classes listed comprise the vast majority of flaky test failures. This is common. The top test class in particular looks like it needs attention. Let's drill down to see what's going on with this test class. Now we can see the outcome and performance trends of this test class near the top, and a list of the most unstable test methods below. Focusing on the outcome test trend, it looks like flaky failures increased sharply 4 days ago. We want to know if this is a new problem or a recurring problem. So let's configure the data filters to show the past 90 days and then refresh the view. Checking the outcome trend chart again, we see only 2 weeks of data was returned, but we've been collecting build data for longer than that, which tells us that the test class was introduced 2 weeks ago. Let's hide past and skipped outcomes to get a better look at the trend. It had no prior flakiness, so it looks like this test class became flaky around 4 days ago. Down below, we see the tests in this class listed by flaky failure count. Only one test method is flaky, which indicates that there might be something unique about this test that triggers flaky behavior. Now, since we've already narrowed down the issue to a single test, let's see if we can spot the problem in the test logic or the related service logic. This test looks similar to other tests in the class. There's nothing obvious yet in the test or service logic that points to the source of flakiness. We can run it, but we're probably not going to be lucky enough to reproduce it that easily. Indeed, it passed, so the flaky failure is going to be tricky to reproduce. Luckily, we can look at past flaky failures to help us figure out what's going on. Back on the test dashboard, we find and click the test row to analyze it. Now we see the outcome and performance trend charts for this single test near the top, and a list of recent failed and flaky test results below. Unlike the test class, however, the outcome trend chart only shows history for the last 4 days, which tells us that this test was introduced 4 days ago. Furthermore, we can see that it's been flaky the entire time. A quick look at the performance trend chart doesn't indicate any changes in test execution duration. We can see that the mean execution time is 14 seconds. We can use this data point to determine if flaky executions are meaningfully faster or slower to better isolate the root cause. Below the trend charts, the most recent failed and flaky test results are listed, each with build-related information such as which task executed the test, the build host, and custom tags. Scanning the flaky results, we see that they seem to occur only on Windows build hosts on CI. Let's compare flaky test results to successful ones by toggling all outcomes. Now you see that flaky test runs take much longer than successful ones. This tells us that there might be some deadlock or race condition causing a test to time out. Let's look at the most recent flaky test run. Clicking on the test result shows more details about the test within the relevant build. Here we see the test path and test outcome at the top, and outputs of 2 test executions below. The test failed and then passed, so it was labeled as flaky. The failed test execution shows the exception with a message and a stack trace summary, which contains stack frames most relevant to this test. The stack trace doesn't give us any clues this time. We can expand the stack trace summary using the arrow, and collapse it again. Let's compare the output between failed and passed executions. If we can identify a difference, it might lead us to the problem. Indeed, the passed test execution has an additional line of output, location db read complete. Let's see where this is coming from in the source. Okay, we found that the output line is coming from this application initialization logic. The test dashboard data previously indicated that the test is flaky only on Windows. This block is reading the location data asynchronously, so I'll bet that the application is serving requests before the location index is populated. Asynchronous code is one of the most common causes of flaky app and test behavior. In this case, the flaky test was caused by a race condition in the application startup, not because of flaky test logic or infrastructure. In many cases, flakiness can be traced to production code, which is why prioritizing and fixing it is a business problem. Because of the volatile nature of flaky tests, we can't be sure a flaky test is really fixed until it has passed a number of times in various environments. So we check back in a day or two. If we forgot to bookmark the test analysis page, we can just simply search the test class by name. Then we can either scan the test list below or search the test method name to see its history. Now the outcome trend for the test shows it's reliably passing since our fix, which gives us confidence that the problem has been addressed. You can also observe that the performance chart shows a drop in execution time as well. This is how you can use a data-driven approach to identify a flaky test, assess how it impacts your project, then isolate the root cause of flakiness, leveraging Gradle Enterprise. Now I'm going to show you a second example, demonstrating how you can use Gradle Enterprise to identify unstable infrastructure in a Java application built with Maven. Suppose we're in charge of the authorization services in a monolithic codebase. We want to be able to deploy from the stable branch on demand, so we regularly monitor tests we own. First, let's filter test data to show results from CI builds on the stable branch from the past 7 days. To analyze authorization tests, we can use a glob pattern to match Java packages we own. Now the outcome trend chart indicates an increase in test failures starting a couple days ago. Looking below, we see that the top 3 test classes cause the overwhelming majority of failures by looking at the red gauges. Let's analyze the top test class, Identity Provider End-to-End Test. Here we see test failures increased significantly 2 days ago, giving us a hint when the regression started. Let's hide the skipped and passed test outcomes so the trend is clear. We see several test methods failing often, which indicates that something common to all of them, such as infrastructure or common code, might be the cause. Next, let's drill down into the top test, which has the highest failure rate. Same story here. The test started failing 2 days ago according to the outcome trend. Scanning the failed test results below, no obvious failure patterns emerge. the failure seems to occur on a variety of CI agents. Perhaps we'll learn something by looking at one of the failing test executions. Looking at the build scan, the failed test exception tells us that it couldn't create a new file because there were too many open files. Perhaps either the test is creating more files, file handles are being leaked somewhere, or something in the test environment changed. Let's check for changes to the test around 2 days ago on the stable branch. We find no commits in the source and test package according to the Git log. So let's see if something in the build environment changed. We can look at captured infrastructure data in the build scan to get a sense of changes to the build environment. Here we see these values fit what we'd expect for our CI instances. The custom values show the build ID, build type, and git commit ID. If there was a change, we can verify this using Gradle Enterprise build comparison. Click Compare Build Scan in the navigation, which will take us to the scans list, where we can find a similar build for comparison. At the bottom of the screen, we see the build we were just viewing. Now we should filter builds to the same project, branch, and build type. We should also set a narrow fixed date range so we can be sure to find a passing build from just before the regression. After clicking refresh, we get a list of passing builds to compare. When we hover over a build in the list, a comparison icon appears. When we click it, the build appears at the bottom of the page next to our failing build. Then we can click the Compare button to invoke build comparison for these two builds. This comparison view will show us differences in the build inputs and the build environment between our passing build before the regression and the failing build after the regression. The blue dots next to the navigation items indicate where there are differences. We see that there were no differences in goal inputs or dependencies, but there were differences in custom values and infrastructure. Looking at the custom values comparison, the only differences we see are the build and commit IDs. Let's take a look at the infrastructure differences. Here we see that the failed build had different JVM memory limits and a higher number of CPU cores. There definitely was some type of environment change that we weren't previously aware of. Now let's search the Git log for commits affecting our Kubernetes or Docker config files. It looks like there was a change to Jenkins container configuration. In the commit diff, we can see that the unlimit flag was lost, which would cause the system to run out of file descriptors while the test ran. Infrastructure is a common source of test reliability problems. In this case, trend analysis helped us quickly narrow down the cause. Now that we've identified a possible fix, we can wait a bit and check the test dashboard to see whether the situation has improved. The next week, we can see that the failed test trend has dropped significantly, indicating that our fix worked. It's very likely that this problem affected other teams in the organization too. What's more, we were able to eliminate a major source of noise in our test suite. I hope you can see now how to take a data-driven approach with Gradle Enterprise to identify flakiness in your test suite, prioritize which tests to address, and fix the most damaging problems so that developers can focus on shipping. Now, if you liked this video, I suggest you check out the Build Failure Analytics video, in which we identify and fix disruptive build failures. There's much more to Gradle Enterprise, though. You can learn about tools which make software builds much faster as well as more reliable in the demo video. Or you can simply try Gradle Enterprise Analytics and let the data speak for itself. Just click the link below. Thanks for watching.